Collisions are at the heart of Chapter 6, at least in my opinion. And there are a couple of extreme cases for collisions that we focus on. One is the perfectly inelastic collision, or the PIC. And in this case, two objects collide and then stick together. That actually is a simplifying factor, so the PIC problems tend to be pretty straightforward. Let's see what we have here. In the initial case, two objects drawn moving together. That's the way we normally think of collision, so I've drawn it that way, but it doesn't have to be that way. It could be that object 2 is moving to the right, and object 1 is moving to the right just faster, and so it ends up being a rear-end collision. And then older cars, at least the bumpers might hook together, and you really would have a perfectly inelastic collision. And the final time, the two objects stick together and form a new object. The M3, that new mass, however, is just going to be the sum of the separate masses, the M1 and the M2, so M3 equals M1 plus M2. I think that'll show up in just a second, and moves off with some final speed. Now, to be honest, without knowing the numbers here, I don't know if in the final situation it's moving to the right or to the left. We'll let the math handle that for us. And there we go. The M3 is going to be M1 plus M2. Haven't put any concrete values in it quite yet. Let's continue looking at it symbolically, at least for the moment. When we do put concrete numbers in, though, of course, here we have our positive direction specified. I'm going to let to the right, as I usually do, be the positive direction. Collisions are all about conservation of momentum. But anyway, we need to look at the momenta, the momentum of each object. So the momentum of object 1, of object 2, and of object 3. All the motion here is in the x-axis, so we're going to focus on the x components. Momentum, of course, is mass times velocity. So we can write that out. Mass of object 1 times velocity of object 1 as an x component, and so on. And finally, that M3, well, we know it actually is the same as the M1 plus the M2. So here we have the momentum of each object. Conservation of momentum, though, says the total momentum initial equals the total momentum final, or at any time in between. The caveat is that it has to be no external forces acting on the objects. So if gravity were pulling the objects down or something, we'd need a little bit different mathematics to get where we want to go. Anyway, so total momentum, we're going to add the momenta, and it'll equal the total final momentum, but that's just for the one object. And this is conservation of momentum, COM. I like the acronyms that appear in this chapter, or at least in my notes. Now let's put in some concrete values. So our objects are 4 kilograms, 6 kilograms. Add those together. Tells us our combined object is 10 kilograms. Suppose the 4 kilogram is moving 7 meters per second to the right. The 6 kilogram, 4 meters per second to the left. And in the final, well, I had to draw something, the object, have it going to the right, but I'm not actually sure, still not thinking about it too hard, which way it's going to go. It looks like it's going to go to the right. We'll see if the math bears that out. Here in the third line, I've put in the concrete values now. So we have 4 times 7, mass times velocity, plus 6 times -4, so the signs are significant here. These are vector components. So mass times velocity is going to equal that total mass times its velocity as a component. And just zooming into the answer, you could work out what's on the left, divide it by 10, so that hopefully our final velocity is going to be 0.4 meters per second. That's a positive value in a vector component. It tells us that the object really is moving in the positive direction. So there we have a perfectly inelastic collision problem.